just kind of review what it was that we talked about on Wednesday. So let me back up just one more. So 30% increase in output is what we get whenever we increase our kVp by 15%, right? So that's output from the X-ray tube. It only goes up by about 30%. 40% would actually double the output from the X-ray tube, but the 15% only gives us about 30%. But that 30% gives us greater penetration, and that penetration is what doubles our image receptor exposure by a factor of 2. So we talked about all that, and then we talked about just the relative change, and that 15% giving us a doubling of the exposure. That's an exponential change, right? So 15% gives us 100%. And I've kind of jokingly referred to that as toilet paper math sometimes. 15% gives us 100%. You go to the grocery store or Walmart or whatever, you walk down the toilet paper aisle, and what do you see? You look at the toilet paper. Have you noticed? It says, it has like 4 rolls equals 16 rolls. What does that even mean? It got exponential toilet paper. But that's kind of what we've got here is toilet paper math. 15% equals 100%. So it's exponential. All right. So and really what we've got there is not an increase, as much of an increase in numbers as what we have as an increase in transmission. And we're going to recycle that. I'm going to show you a graphic here in a bit that shows that we use a shortcut in kind of explaining the relationship between kVp and image receptor exposure, right? Because we say as kVp goes up, scatter goes up. But what did we learn? That as kVp goes up,
penetration goes up.
all
up.
interactions go down, but what we get is a higher percentage of scatter photons penetrating through the patient. And it's really that penetration that gives us that increase in scatter. It's not truly an increase in scatter, it's an increase in transmission of the scatter and incident on the image receptor. So that is really pretty much the summary of what we talked about on Wednesday as far as kVp and scatter goes. It's also a summary of what we're going to talk about today and re-look at today, all the way down through where we get to interactions inside the patient and different tissue types. So we're going to talk about that here in a bit as well. So the wording was confusing, but really what we're looking for here is transmission through. So the context then is that increase in kVp alone does not just lessen the amount of radiation absorbed by the patient. You got to consider the entire beam, right? So, and we took a look at that. As we increase our kVp, those low energy photons that would have absorbed inside of the patient anyway, as we increase kVp, we're going to get more of those, and those are still going to absorb inside of the patient. These are going to be kind of a mixed lot, and then from this point up is where we truly get to the point where as kVp increases, all interactions decrease. So two things can be true all at the same time, right? So as kVp increases, we get an increase in penetration and all interactions decrease, right? But in the as we increase kVp in a given X-ray beam, patient dose is going to go up because we're going to have all these low energy photons. So where you should be looking for test questions that address those things is, if you saw a test question from now all the way through the registry, and the test question said as kVp increases, as kVp increases, selection choices, all interactions decrease. It's absolutely a true statement, right? So the second thing you should be looking at is, further down, is there some but not all of the above or an all of the above? Because B might say as kVp increases, patient dose increases. Is that true? Yes. So both of those things are true at the same time. What you should not have is 4 separate answers, one not including, some but not all the above, 1, 2, and 3, or anything like that, and those 2, okay? So, in your test questions, always look for that, maybe even make that your first look. Look at the last answer and see if there's a some but not all the above or an all the above, and then start picking through them. I'm not always going to give you, some people think that every time they see all the above, that's got to be the answer, and that's not going to be the case. So look and see if it's there, but then start evaluating your other answers, if that makes sense. So, again, what all it means is multiple things can be true at the same time. As kVp goes up, the new added higher energy photons and the higher energy photons that were created will still likely to penetrate, but we're still got those low energy photons that are going to absorb in the patient. So yes, patient dose is going to go up, but yes, all interactions are going to decrease. So on a percentage-wide basis, overall, we get more penetration with a higher kVp, right? And we also get a higher percentage of what comes out of the patient being scattered, okay? Even though the scatter truly doesn't, isn't created at a greater rate, we get more penetration through the patient and we get higher scattering. What you got?
At the IR, right?
At the IR, yes,
IR
thank you.
less in the patient.
Yeah, at the IR, that's emitted. Okay, so you've got 2 emissions, one from the x-ray tube, right? That's your 30%, and then you got emission from the patient, and those are your image-forming x-rays, and that's what we're talking about.
That's where it
for
doubles.
penetration.
That's where it doubles with 15%.
Bingo, that's where it doubles with 15%. We don't get the double above the patient, we get the double under the patient. Right. Okay? So, I just kind of threw some numbers out here, and again, you're never going to create an X-ray beam that only creates 90 photons. But let's say with the 2 X-ray beams of Bushong, in Bushong's example, we create 90 photons, and let's say at 72 kVp, we get an even distribution of absorption, scatter, and penetration. As we increase to 82 kVp, notice what happens to our photoelectric absorption goes down. Now I want you to keep this in mind. Notice I didn't change the numbers on scatter, and I'll explain why. We pretty much already have. The kVp is not going to affect it that much, but we're going to, again, take a look even deeper into it here in a bit. So we get 60 penetrating through the patient, which, with our 15% kVp, increase in kVp, we doubled exactly the number of photons penetrating through the patient, right? Notice that if we add all that up, we've got 90 photons over here, and over here we've got what? That'd be 117. There it is, 117 photons. So we got the 15, and that's 15% greater than 90 is what that is. So 15% increase in photons, we got pre-patient, we got a doubling of the photons post-patient. So we double our image receptor exposure.
That's without changing mass, right?
That's without changing mass. We're going to get there in a bit, yeah. So at 72 kVp, you had a third of each. At 82 kVp, a much higher percentage of the X-ray beam penetrated through the patient flesh. And the absorption and scatter, it's going to change some. When we get to adjusting our mass, you're going to see really how it is that we can use kVp to affect the change in patient dose. So the amount of absorption is relative to the amount transmitted, and scatter is decreasing.
Does it do that because when you up your kVp, it ups the total amount of photons? Is that why you can absorb more and scatter more?
Yeah. As you increase if the only thing that you increase is your kVp, yeah, you're gonna, all of that is gonna go up, right? Percentage-wise, they may go down, but raw numbers are gonna go up. Okay. All right, so claim number 2, increasing kVp increases patient dose, and we just hit that. That's absolutely true. The only thing that you're increasing is kVp, patient dose is gonna go up. It's gonna be fairly dramatic. It's not gonna be as dramatic as doubling of the mass, but if you increase your kVp by 15%, you increase the number of photons that you emit from the tube by about 30%. Some of those are gonna absorb inside of the patient. But what we're gonna wind up with is a doubling of the image receptor exposure. So if you need to make a change to your image receptor exposure, you make an exposure, and your index number indicates that you underexpose the patient, then what you can do is use kVp to adjust for that. You can increase your kVp by 15%, that would double your image receptor exposure. Unfortunately, patient dose is gonna go up too, but it's not gonna be as dramatic as doubling the mass. There's two different ways that we can, really more than that, but there's two ways that we're gonna talk about today that you can increase the image receptor exposure. One is with mass, which is the industry standard preferred way to increase the exposure, image receptor exposure. I think there's gonna be a shift in that. I think we're gonna go more towards kVp, the more they improve digital imaging. But for right now, it's primarily mass. But you can also use kVp to accomplish the same thing. So unfortunately though, our dose is gonna go up. We're gonna look at why I think that we're gonna move more towards kVp than mass here in a bit. So since an increase in kVp increases output from the X-ray tube, dose will increase. Now you're still creating those low energy X-ray photons. Everything shifts towards a high energy side, but you're still creating those low energy photons. So in our example, just to keep it simple, we're gonna say dose is increased by 30%. So if you were to double mass, how much would your patient exposure change? Double. It'd be double, right. So higher kVp then is a more patient-friendly means of adjusting your image receptor exposure. So more on that here in a bit. So claim 3, a 15% increase in kVp equals a doubling of mass. We've already debunked that. It's true in context, but the context is where is that double happening? You're not getting a 100% increase, a factor or 2 increase emission from the X-ray tube. You're getting that at the image receptor, right? So doubling of the mass means doubling the tube current, doubling the photons created, and that's not what we're getting with the change in kVp. So if we double the number that we created, then we would double the number emitted from the X-ray tube, and that's mass. But with kVp, as we increase kVp, we get about a 30%, 15% change in kVp, we get about a 30% increase in output from the X-ray tube. So 15% increase in kVp did not double tube output, only increased by about 30%. The change will, however, result in a more penetrating X-ray beam. Unfortunately, scatter is going to be a part of that penetrating X-ray beam. So we're going to have more penetration without interaction, and we're also going to have more penetrating scatter radiation. So back to those two questions. As we increase kVp, do all interactions go down?
Yes.
Yes. And as we increase kVp, does scatter go up?
Yes.
Yes. Scatter penetration, not scatter creation, scatter penetration. Okay? Big difference between the two.
So if you ask if scatter creation goes up, it's false.
It would absolutely be false. Yep. So the context there is 15% increase in kVp doubles image receptor exposure, but not patient exposure. So can kVp be used to change image receptor exposure? Well, we just talked about that too. Yes, is the answer. So how much of a change do you want to make? What are your rules for mass and your changing of your image receptor exposure for mass? What's the minimum you want to change? There's two rules fundamentally. What's that?
Up or down by 2, yeah.
Okay, that's one of them. You're gonna if your image is worth repeating, if it's worth going back in and shooting the patient a second time, then the change in mass that you need to make is a factor of 2. That's your starting point, is a factor of 2, really. All right? Just to see any kind of change at all, and this was even on film, and it's less obvious with digital processing, the baseline is 30%, but if it's worth repeating, it's a factor of 2. Okay, so what's a factor of 2 in kVp? 15%, right, exactly. So if you need to repeat and you need to use kVp, let's say you're doing a pediatric patient, they're more radiosensitive than adults. You're doing a pediatric patient, you don't want that patient to get, a full doubling of the dose. You already dosed them once. You don't want to go back in and give them twice the dose. Now they got 3 times the dose. You could increase your kVp by 15%. So the other one, the baseline, it really doesn't apply anymore because it's such a minimal change on the image receptor, is 30%. So what is 30% in a percentage of a whole, in a fraction? What is that roughly?
33.33.
33.3 is roughly a third,
Yeah.
right? So what's a third of 15? 5, right. So the change in kVp to equate to a 30% change in mass would be 5. Right.
So go from like 75 to 80.
Right. Well, it's 5%. So 5% of let's say 70, just to keep it easy, would be 10%. Yeah, 3.5. So it'd be 3.5.
But do you change the mass too?
Not if you want to make a change at the image receptor. All right.
Would it
So
have the same effect as if you would have?
yes, it would have the same effect. If you change 5% of your kVp, it'd have the same effect as a 30% change in mass.
Oh.
Okay? All right, so claim 5, increases in kVp decrease patient dose. Yeah, it does, but we just talked about if you increase kVp, you increase patient dose, but how can you use kVp? If you increase kVp by 15%, you get 30% increase, roughly, in the number of photons that you create, right? And that's gonna double the image receptor exposure. Okay, so now you gotta go back in, you made one exposure on the patient. Again, it's a pediatric patient. What do pediatric patients do? Squirm, they move all over the place, right? So you gotta go back in, you gotta make a second exposure. And you don't wanna double dose the patient. Let's say your technique was perfect. Your index number showed that you were right where you needed to be. But you gotta repeat because of motion. But you don't wanna give the patient a full another dose. Plus, and this is getting ahead of us, into another thing that you can do with kVp. What can you do?
Increase your VAS.
Okay, you increase your kVp by 15% and reduce your mass. Now your patient dose is going to go down, right? You only increase the number of photons that you created by 30%, but in cutting your mass in half, what happened to your overall number of photons you created?
Down.
It went down, right? So the patient dose is going to decrease. Well, let me finish this thought real quick first, because it might answer your question. In addition to that, if you're cutting your mass, what are your 2 factors in mass? MA and time, right? So what's your patient population that we're talking about in this example?
Kids.
A squirming kid,
So you
right?
get your time.
Reduce your time. So that's another thing. Can you use kVp to reduce time?
Yes.
The answer is yeah. The answer is absolutely yeah. Okay, so, and this is jumping again back down to all the other stuff at the bottom of the PowerPoint. What if you phototime? How do phototimers work? They're automatic, right? They read the amount of radiation coming through the patient. They send a signal over to the timer circuit to discontinue the exposure, right? So if you phototime and you increase kVp, what's going to happen? Increase penetration and what? shorter. You're just gonna get to your exposure a whole lot faster. It's gonna terminate the exposure a whole lot faster. It works the 15% rule for you. Okay? So, Zoe, your question,
I was
if you haven't
just-
forgotten it.
Okay, so you said whenever you increase kVp and decrease mass, patient dose decreases.
Correct.
If you only increase kVp,
Patient dose increases.
increases. Okay,
Yep.
just
Yep.
making sure I had it.
Yep.
So could you keep your MA the same, but just change overall mass by lowering the exposure time?
Exactly.
Okay.
Yep. So you're shooting tabletop with a kid, you increase your kVp by 15%, you just reduce your exposure time by by a factor of 2.
Mhm.
Yep. Okay. So everybody good with this? So kVp can both increase or decrease depending on what you're doing with your mass. So how are these questions gonna come at you? Pretty much like that, what are your options for shortening exposure time? You can increase MA and decrease time, and we call that the law of reciprocity, right? Give and take. Or you can increase your kVp, and that's gonna enable you to use a reduction in time to reduce overall mass. If you're phototiming, you increase your kVp, and your mass is naturally gonna go down. It's gonna work your 15% rule for you. So you're gonna look for things on your test question. What happens at the image receptor and what happens inside of the patient, right? So reduction of exposure time using kVp is 15% rule. Increase kVp, reduce mass by a factor of 2, specifically time. You want to increase the exposure to the image receptor just using kVp. What are you doing? Just increasing kVp. You want to reduce patient dose, then what are you going to do?
Increase kVp.
Increase kVp by 15%, reduce mass by a factor of 2. Now, your sophomore year, we're going to, I told you you're not going to be doing a whole lot of math on this test in this semester. The things that you might do you really don't have to do any math, but we may work the 15% rule, we may work the inverse square law, direct square law, but the things that you know about those things, you can answer the questions without putting a pencil to it. All right, so you can have a calculator if you want to, but the answer is going to be pretty obvious. In your sophomore year, we're going to get real deep into this, and there are going to be things like, okay, so you want to increase patient exposure, or you want to increase image receptor exposure while simultaneously reducing time, so you're going to have to do multiple, increases and decreases. That's not this semester. That's going to be your sophomore year. So it's not going away. So just looking at it by the numbers, again, we've got 72 kVp, and what we've got here is we've got an increase, so this is basically the same thing. I've just put this little asterisk out here just to say that scatter changed by a little bit, but it didn't change much. It did decrease. More on that here in a bit. So we've got a double of the image at the image receptor, right? So this is our overall technique, 72 kVp versus 82 kVp, both with 2 mass. Now look what happens when we reduce our mass though. We've still got 30 transmitted to hit the image receptor, but what happened up here inside of the patient? Went down drastically. So the patient dose is going to drop pretty good. Now as patient dose, never mind, I'm not going to complete that thought because it's just going to confuse you. So we've got a reduction of overall photons, less absorption inside of the patient, same image receptor exposure, right? So what's a better dose for the patient? Low kVp high mass or
High kVp.
high kVp low mass, right? All right, so, and that just explains all that. As kVp was increased, the numbers emitted from the tube increased by 30%. Compton remains similar, right? So what really changed though was the PEs, right? We get less absorption. keeping in mind that those Comptons, that we create, some of them will become photoelectrics and some of them will penetrate, right? It's just unfortunate that as kVp goes up, more of those Comptons, penetrate the patient. So P's decreased more rapidly than Comptons, so rolling that back up, we lost more PEs than what we did Comptons. The transmitted beam contains both of those, and we're gonna have to deal with that at some point. And when mass is reduced, patient dose decreased pretty dramatically, right? So claim 6. As kVp increases, all interactions decrease. I think we've done that to death. Do we need to walk through that slide?
That's true, if it's only kVp increases.
Exactly, yeah. So as as kVp increases, what we really get inside of the patient, if the only thing that we change with kVp is only thing we change is our kVp, then the patient dose is going to go up. But as a percentage, what we're going to get is more penetration, right? Penetrated, unattenuated, and penetrated Comptons, right? So as a percentage, we get less absorption, more penetration.
So would you ask as a number, maybe? Like if you, or just?
Probably I would ask more of a percentage. Yeah, as kVp increases, what percentage of your beam, what happens to the percentage of penetration, what happens to the percentage of Compton? They all go down. Or the penetration goes up, but the Compton and the photoelectric go down. All right, now this is where it gets a little bit sticky. Okay, so two big claims about scatter radiation that we make that are just shortcuts. And we say as kVp goes up, scatter goes up. You know the truth now. Scatter doesn't really go up. Scatter penetration does go up, right? But scatter creation does not. The other thing is we say as we change from bone to soft tissue, what happens to scatter? We create more scatter radiation. What kind of tissue? Soft tissue. Right, soft tissue. And that's a lie too. So looking at this, it's true in context, but again, that's a shortcut. And it almost perfectly parallels kVp in scatter creation. So what we've got here is, on the computer it looks a little bit better, but up here it's pretty fuzzy. So what we've got here is number of interactions versus kVp. So as kVp goes up, so we're at 60 kVp, we're at close to 130 kVp there. As kVp goes up, we get more penetration through the patient. So our interactions, just like what we have been talking about, interactions decrease with increased kVp, right? So that's in bone versus soft tissue. It's universal. Okay, but what about Compton scattering in all tissues? If you look at this line, does it change?
Goes down a little bit.
It goes down, but is it nearly as dramatic as those two?
No.
And the answer is no. So, does the tissue type really affect our Comptons?
No.
Compton creation is no. It really doesn't that much. It might just a little bit, but not very much. So why do we say as if we change from bone? Why don't we just say, why is it that we say we create more Comptons, more scatter radiation in soft tissue?
Because scatter penetration goes up.
Bingo. What's easier to penetrate? Soft tissue, bone.
Soft tissue.
Soft tissue, right. So remembering that your Comptons, first off, they interact with the outer shells. This is theory behind it. They interact with the outer shells and they lose energy. The X-ray photon loses energy with each one of those interactions. So what you have in bone is very dense, tightly packed, tissue types, atoms. You got your calcium, you got magnesium, you got phosphorus, you got all kinds of stuff in there that has a higher atomic number than what does hydrogen or oxygen, right? So if the X-ray photon interacts with bone, it's gonna bounce around in a very tight area and absorb much more quickly than what it will in soft tissue. With soft tissue, we're gonna have more penetration through that soft tissue. So again, do we create more Compton in soft tissue?
No.
In a measure of soft tissue, if you had an inch of bone and an inch of soft tissue, no. You're not gonna create much more. But what's gonna happen in the bone?
You're gonna absorb more.
It's gonna absorb, Compton's gonna absorb, and you're gonna have less penetrating through the patient. So again, we're back to post-patient, what's going on? We have more absorption in the bone, so we have less transmission through the bone. The bone stands out, the soft tissue just makes a fuzzy gray mess, right? So with that in mind, we'll get into it. With increased kVp, all interaction types decrease. Photoelectric decrease at a much more rapid rate than Compton. Compton remains fairly unaffected by kVp or tissue type. Low kVp will create higher rates of photoelectric in all tissue types. High kVp, low rates of photoelectric. So again, the higher the kVp, the more penetration we have, including scatter. Low kVp will cause low energy Comptons to become PEs, right? So they stop, they become PEs, they don't make it through the patient. High kVp will cause more penetration of all those. So using the 15% rule, you kind of see how it is that all this stuff comes together. So we've got a 15% increase, and that's an important distinction too. Most of the time when we're talking about 15% rule, we're talking about saving patient dose. So 15% rule by definition is 15% increase in kVp, half max. If you want to increase differential absorption, you want, in today's world, I don't know why you would want to do this, but if you did want to increase differential absorption, you reduce kVp by 15% and you would double the mass. Exactly, right. So with that, you can see how 15% change, reduces patient dose. So increase in kVp increases scatter, true in context and all the context that we talked about before. It doesn't change the scatter we create, it changes the scatter that's emitted. So is it wrong to say we increase kVp, we increase scatter?
No.
Not as long as you understand the whole concept. You don't really increase the amount of scatter you create, you increase the amount of scatter in the remnant beam. Those image forming x-rays, you're gonna have a lot of scatter with increased kVp.
So how would you ask that, look for that on a test? So we look for, if you increase kVp, what happens to scatter creation?
It goes down.
Down.
Yep.
But if you increase kVp, what happens to scatter post-patient?
Or at the image receptor,
It would go up.
It would go up.
Okay.
Right. Yep.
So scatter creation would be in the patient.
Scatter creation would be in the patient. Yep. Yep. So scatter at the image receptor is going to go up. Scatter in the patient is going to go down. So the remnant beam is going to be, composed of both unattenuated, penetrated photons and that scatter radiation. As kVp goes up, both of those go up. It's not that you created more, it's just that you emitted more. So the ratio of PE interactions relative to Compton's changed. That's what we refer to as the PE ratio, or Compton to PE ratio. So what happens as we increase our kVp is the Comptons remain pretty consistent, right? Looking at that previous graphic, the Comptons remain pretty consistent. So if we had an X-ray beam that was just all Compton and 50% Compton, 50% photoelectric, as we increase our kVp, what's going to happen is the Comptons remain the same, but the photoelectrics go down, and we'll get penetration, right?
Mm-hmm.
So that's what we're referring to in the Compton to PE ratio. Is as kVp increases, we get not really more Comptons created, more emitted, but what decreases very rapidly, going back to that graphic before, is photoelectrics. These are all photoelectric interactions. as kVp increases, you get great penetration through all tissue types. You know, we get down here to, 130 kVp, and according to this, is not necessarily 100% accurate, but at 130 kVp, you get no absorption in bone. At 60 kVp, you get no absorption in soft tissue. You will, but, just for a visual. Okay. So, a lot of quotes from this point forward, and the Fauber book, I think, kind of sums up everything that we've been talking about best, and we'll get to that here at the end. If we can get through, I think we can get through this today. So, with increased kVp, more X-rays are emitted. They have higher energy and greater penetrability. Unfortunately, because they have higher energy, they also interact more by Compton effect and produce more scatter radiation. But then it goes on to say the probability of a given X-ray will undergo Compton scattering is a complex function of the energy of the incident X-ray. In general, the probability of Compton scattering decreases as X-ray energy increases. So they seem to be contradictory, and this, is part of the problem. They seem to be contradictory. So what he doesn't really explain well is the penetration of the Compton versus what's actually happening at the molecular level. So using higher kVp reduces the total number of interactions, it should be and increases the amount of X-rays transmitted. In these interactions, Compton scatter increases, photoelectric decreases, and more scatter exits the patient. And that's the key, is not so much that the Comptons truly increased in number, it's just that they exited the patient. At higher kVp, more X-rays are transmitted with fewer interactions. This is out of Fauber. However, a greater proportion of the interactions are from Compton than from the photoelectric absorption. As X-ray energy increases, this is back to Bushong, X-ray energy increases, the absolute number of Compton interactions decrease, right? Because as kVp goes up, all interactions decrease. So as X-ray energy increases, the absolute number of Compton interactions decrease, but the number of photoelectrics decrease much more rapidly. Therefore, the relative number, and maybe better stated percentage, of the X-rays that undergo Compton increases. That's the increase in the beam post-patient. Okay? It's an emitted beam from the patient, not from X-ray tube. So what you get then is, again, as kVp goes up, Comptons remain fairly stable, and photoelectrics drop. So if you're at 50-50, right? 50% Compton, 50% photoelectrics. If you increase your kVp, the photoelectrics drop. The number of Comptons didn't change. Let's say our photoelectrics are now 10%, right? The number of Comptons didn't change, right? But the percentage is now what? If photoelectrics are 10%, what's our percentage of Compton? 90, right. Okay? So
in the PE ratio, whenever we up the kVp, photoelectric percent goes down, but Compton goes up.
The percentage of Compton goes up. Yeah. The numbers don't change significantly, or the percentage changes. Yeah. The numbers actually go down. The percentage goes up. So in photoelectric effect, we've got X-rays in diagnostic range undergo ionizing interactions with the inner shell. So this photoelectric outer shell is your Compton. The X-ray is not scattered, but is totally, I stuttered on that, absorbed, and that's called your photoelectric effect. So then you flip over to the top of page 159, the probability that a given X-ray will undergo photoelectric interaction is a function of both the X-ray energy and the atomic number with which it interacts. Photoelectric interaction cannot occur unless the energy is equal to or greater than electron binding energy. Where's the electron binding energy going to be greatest? Inner shell, right. So back to our solar system model that we talked about last semester. The closer to the nucleus, the more tightly bound they are. So it seems to suggest that the likelihood of electromagnetic interaction increases with increased kVp, but it really doesn't. Probability of PE is inversely proportional, and this is pretty significant. Inversely proportional, what does that mean? One goes up, one goes down, right? So it's inversely proportional to the third power of the energy. So as the energy goes up, interaction goes down, right? And then if you look again in your Bushong book, it's the second penguin, it says probability of PE, photoelectric interaction, PE, is directly proportional to the third power of the atomic number of the absorbing material. Okay. But we just said that the absorbing material doesn't really change comptons, right? So it changes photoelectric because those comptons are going to bounce around and become photoelectric. It's also going to, the atomic numbers are going to be low enough that, say, 100 kVp X-ray beam is going to far out exceed the inner shell binding energy. So is it going to stop on that electron, inner shell electron? The answer is probably no, but it's going to lose some energy, and might it stop on the next one?
Yes.
Yes, and then it becomes a compton. Or I'm sorry, then it becomes photoelectrical interaction. All right, so as kVp goes up, PEs decrease. As atomic number increases, the PEs decrease, and you get more penetration. But what about the scatter? So, I forget what page this was on. Bushong comes, I don't know that he does anymore. He's getting older. But if he comes through and does a lecture, I highly recommend that you go see him. He's a funny guy. He really is. He's funny. He's got a lot of character. But he adds little, Easter egg jokes in the textbook that if you don't really understand Bushong, if you've not seen him, you kind of miss it. There was a movie, it was called Straight Outta Compton. All right?
I saw that and I said, no.
That was his bad dad joke. All right? So the whole thing about milk and magnesia in the, I don't know, one of the first chapters, where, magnetism was discovered, and he said that all the cows in the area give milk and magnesia. You have to go back to one of the first chapters. Yes, they give milk and magnesia because they're cows in magnesia. They don't give the laxative milk and magnesia. That's Bushong. All right. So X-rays can undergo interactions with outer shell electrons, and that's where you get your comptons that not only scatter, but it reduces the energy. It ionizes the atom, but it reduces the energy of that X-ray photon. So it hits multiple outer shell electrons. It's going to lose energy with each one of those interactions until it eventually becomes PE, exactly, photoelectric. All right, so the X-ray continues with less energy until it either penetrates the patient or hits an electron it can't eject. So usually the scattered X-ray retains most of its energy, both the scattered X-ray and the ejected Compton electron. They still call it Compton, even though now we're talking about electron and not a photon, have sufficient energy to go on and further ionize different atoms. So if you read through Bushong 157, the first sentence seems to suggest that no scatter exits the body. But if the photon undergoes enough comptons and lose enough energy, ultimately they will become photoelectrics. If they don't lose that much energy, they'll penetrate, and as they penetrate, they fog the film, or they fog the image receptor. They become scatter radiation that hits the image receptor. Okay? See the difference there. Creation versus, incident on the image receptor. So, I'm not gonna spend a whole lot of time on this, but you can see that as kVp goes up at 50 kVp, most of your interactions are gonna be photoelectric, especially in bone. Compton, and this is a percentage, the Comptons are gonna be relatively low, but as we increase kVp, we get less photoelectric, and our Compton dominates our total interaction. We get a total transmission, and our total interactions inside the patient go down as well. Okay, so this would probably be better stated. I'll just leave it at that. I just want to confuse it. All right, and that's basically what this says. Is at 50 kVp, 79% of the X-ray beam interacted by photoelectric, and 120, only 18% did. So at 21%, at 50 kVp, 21% are scattered. At 120, 83% represents your remnant beam. So at 50 kVp, less than 1% exits the patient. At 120 kVp, we've got our total transmission is at 9%, and that's Compton and unattenuated. Okay, so as kVp goes up, we get more penetration, and we get more Compton penetrating through the patient, even though the number of Compton interactions decreases. We get more penetration. Okay, so this is kind of preface to what we started this with the discussion on tissue types. All right, so atomic number, K-shell binding energies is on table 1.2 and 1.3 in Bushong. So our atomic number of oxygen is 8 and calcium is 20. So what causes the interactions inside of the patient? The photon hits a electron. So which one has more electrons? Which one has a higher binding energy on the inner shell electron? Calcium. So again, as the atomic number goes up, our Comptons necessarily change, and the answer is no. What we get, though, is more of those Comptons that become photoelectric because of that higher binding energy. If they bump into it, it's kind of like, you've been to a football game, right? What do they do at the start of a football game? Before the kickoff, they run through the banner, right? They run through the banner, right? So, there's your banner. It's more like a brick wall. You're just not going to run through it quite as easily. So, our effective atomic numbers, and you're going to get into this probably in rad bio, but we're also going to talk about it in imaging, right? Bone is not an element, right? You don't find it on the elemental table. You don't find fat on the elemental table either, right? So what we're talking about is effective atomic numbers. So you take all that stuff, all that goo that the bone is made of, and also the soft tissue, and you kind of put it together, and these are the effective atomic numbers. And what you'll hear that referred to as Z number. Z number we may use that to refer to atomic number too. And they may say ZEF, Z-EFF. That's Z effective, and that's what these are. Okay, so fat, the effective atomic number of fat is 6.3. Soft tissue and lung are the same at 7.4, and other soft tissue and lung 7.4, and then bone is quite a bit higher. Okay, so this I pulled off of what's the website? It's System, Press Books Pub, I don't know. So kilovoltage is the exposure factor to determine the proportion of scatter radiation reaching the image receptor. That's the big thing, reaching the image receptor. Low kVp beam has more photons with low energy, and those are more easily absorbed by the atoms of the patient's body. So they absorb, right? Even if they scatter, they absorb. A photon that has already been absorbed can't be scattered, so it stops. The patient receives all of that dose at the photoelectric. As the energy of the photons in the X-ray beam increases, all type of interactions within the patient's body that attenuate the beam decrease. Okay, so that's what we've been talking about. kVp goes up, all interactions go down. But overall, increase in kVp decreases the probability of X-ray interacting within the patient's body, but the rate of photoelectric absorption photoelectric interactions decreases faster than the rate of Compton scattering. That's our PE ratio. So as kVp goes up, PEs go down, and Compton goes up, not in numbers, but in percentage of the remnant beam. Okay. All right, so this is over dramatized, your exposure. If you were to just use an absorber, homogeneous absorber, you just take water, you put it in a tub, you make x-rays of it. As kVp goes up, then our PEs are gonna go down, right? Our Comptons remain relatively comparable. Our transmission goes up dramatically. It's just all that saying all that. All right, so we're running out of time. So let's get to the other stuff, because I really think that, you know, that last two slides we've covered them pretty much in detail. All right, so are there other things that we have to know about kVp? And the answer is yeah. Since high kVp increases scatter to the image receptor, we got to deal with it. So we got to clean it up. So what are our rules for cleaning up scatter radiation? Grids. Okay, grids prevent scatter from striking the image receptor. Unfortunately, they increase patient dose. So there's really two things that truly affect the amount of Compton that you're going to create. One is the thickness of the tissue. I don't mean the denseness of the tissue, the thickness of the tissue. So if you're shooting through, 3 inches of water, you're going to create so much scatter radiation, right? Mm-hmm. If you double that, it's going to create exponentially more scatter radiation. So as we increase the thickness of the tissue, we have more tissue to create Compton scatter. If we have more tissue to create it, we're going to create it. Okay, that's number one. And it's all about exposure of tissue that creates Compton. So what's the other thing then? So we got the thickness of the tissue. What's that? The type of tissue, we already said type of tissue really doesn't matter all that much. It does in transmission, and therefore, since it does in transmission, we may still have to deal with it post-patient. But I'm talking about creation at this point. Exposure of tissue, right? So we got thickness of the tissue. What's the other area that we might expose?
The length of it?
Collimation, beam restriction. If you expose more tissue, either this way or this way, you create more Compton. Okay, you're going to create more scatter radiation. So, why is it that you take an X-ray on a asthenic patient, a KUB on an asthenic patient, and the difference in bone and soft tissue just pops? You can actually see the kidneys. You might be able to see the inferior border of the liver, and it's just real black and white.
Because you have less scatter.
Because you have less scatter. Now you got somebody who's 400 pounds. Have y'all had one of these?
Mm-hmm.
Yeah. What does their KUB look like?
Gray.
Very gray, because it's got a lot of scatter. Right. Right. Because you've taken this much tissue, and now you're exposing this much tissue.
Mm-hmm.
Right. All right. So when imaging soft tissue, a higher amount of scatter will reach the image receptor. It's not created, it's reach the image receptor. As scatter leaves the patient, a significant amount is directed towards the image receptor. We use grids to clean that up, but before we expose the patient, we should be using beam restriction to limit the amount of scatter that we create. Right, so we have two things essentially, collimation and grids.
So you up your collimation and lower your Compton.
Exactly. Expose less tissue, increase collimation, if, you know, there's an inverse relationship. You increase collimation, you decrease field size, right? So grids typically, our rules for grid use are gonna be, 10 centimeters. The Fauber book calls for 60 kVp. I think industry standard is 70 kVp. So if you're using 70 kVp or above, you're gonna penetrate enough scatter that you need a grid. If you're shooting through 10 centimeters of tissue, your tissue thickness is thick enough, you need a grid.